Welcome to Maths with EJD. In this video, I'll be talking about non-convex optimization in two dimensions. I haven't talked about that in one dimension in the previous video. Interestingly, when I was given the practice question, I gave questions bordering on two dimensions. So for the sake of that, I'm going to give practice questions on one-dimensional problems here so that you can try your hands on that based on what I did in the previous class. Okay, so number one, Number one, find the critical points and classify them for f of x equals x raised to power 4 minus 4x cubed plus 6x squared minus 4x, like that. Then let me add one. Say this: identify all local minima and maxima of f of x equals sine x plus x. Okay, those will be practice questions for one dimension. So the ones I gave for under one dimension, you can now use what I'm going to teach in this video to take care of those questions, or I might also repeat them in this place. So let's go ahead and talk about um, convex optimization in two dimensions. Okay, convex optimization in 2D. Convex, convex, sorry, non-convex rather. Non-convex, non-convex optimization, optimization in two dimensions. That's talking about X and Y planes. Okay. So non-convex optimization in two dimensions involves an objective function f of x comma y that is not convex, meaning it can have multiple local minima and saddle points. Saddle points are points that are neither uh, minimum or maximum points. That multiple local minima and saddle points. Okay, this makes finding the global minimum. This makes finding the global minimum challenging. Okay, so for convex functions, right, you can easily find the global minimum and global maximum. But for non-convex, it's not that easy. Okay, so let's talk about the problem definition for non-convex optimization. Problem definition. Okay, so consider the non-convex function. Consider the non-convex function f of x comma y equals x raised to power 4 plus y raised to power 4 minus 4x squared minus 4y squared plus 4. Okay. So the first thing we want to do is to find the critical points. But before we even go for that, just like we did for one dimension, it was important to visualize the function. Now, so I have it written here, but Desmos won't give you this, but you can visualize it if you write it as an equation. So just say this is equal to 0. So you can see the function. If you draw a line, say, okay, I see it passing through the origin. So if I say I want to draw a line, y equals x, you see that? What if I also want to draw a line y equals minus x? So see that going that way. Um, okay. let me delete this and do something else. I want another color. So I want minus x now. Okay, so you see as that it's passing through. So if you draw a line, right, you cannot for sure say it's totally lying within the function because we have the function is not that straightforward. So this is one, right? So if I begin to change it, so say that from 0, if I change it to 1, let's see what you have. Then I have 2, I have 3, I have 4. So maybe from 4, it becomes like a function that even you can't even totally say it is convex because if you draw a line from here to here, it will not pass through the function. So except if the right hand side of the equality becomes really big. But on a normal day, this is just 0, and it's that kind of convex function like that. All right. So coming back here to deal with the problem. So we have seen clearly that the function is actually convex. So, visualizing the function actually is really important in trying to see whether it is convex or not convex. Or you can also use the condition that was earlier stated when we talked about convex functions to deal with that. So step one here is to find critical points. Find critical points, and that usually involves differentiating and setting to 0 as it's right from what we learned in calculus. So to locate stationary points, we compute the first order partial derivatives, the first order partial derivatives. Okay. Of course, we get the function again. That's f of x comma y equals x raised to power 4 plus y raised to power 4 minus 4x squared minus 4y squared plus 4. So we want to get the first partial derivatives. So that means we get partial f partial x. Usually that's like f sub x, like we used in the previous in convex optimization in 2D. So partial f partial x is the same thing as f sub x like this, and that is equal to differentiate this function with respect to x. So you get 4x cubed. That is where you have x. So if you differentiate with respect to x, that will be 0. But when you come here, you have minus 4x squared. So when you differentiate that, you get minus 8x. Then there's no x anywhere again. So every other one goes to 0. So this is partial f, partial x. Okay, and then this can go. Talking about x, 4x cubed minus 8x. Then the other one is partial f, partial y, which is the same thing as f sub y. And that is equal to, this is x, so you differentiate with respect to y, you get 0. Then this is y, you get 4y cubed. Then there's no y here, that would be 0. Differentiate this with respect to y, you get minus 8y. Then this is 4, so no y there, so it goes to 0. So you can, so we are done with that. Okay, so that's partial f, partial y right there. Okay, so with that done, so we since we are looking for critical points, we set them to 0. Okay, um, setting them to 0. Okay, we have the first one that is 4x cubed minus 8x. 4x cubed minus 8x equals 0. So we can factorize x out of that, or 4x. So 4x is common. So we have 4x into x squared minus 2 equals 0. So that simply means that we have 4x equals 0, or x squared minus 2 equals 0. So that means if you do, so we have 4x equals 0, or x squared is equal to 2. And then we have 4x over 4 is equal to 0 over 4, or we take square root of both sides. Square root of x squared equals, square root is plus or minus. So that'll be plus or minus square root of 2. So this cancels. So x is equal to 0, or x is equal to, square root cancels power. And then you have plus or minus square root of 2. Okay. So you have x can be 0 or plus or minus 2. So we have that way. On the other hand, we equate 4y cubed minus 8y to 0. So we say also 4y cubed 4y cubed minus 8y is equal to 0. Again, we have 4y squared common into y minus 2. and that is it into y minus, sorry, not 4y cube. 4y is just common. We have 4y. Let me go back. Okay, that's 4y now into 4y into y squared minus 2 is equal to 0. Again, we have 4y is equal to 0, or y squared minus 2 is equal to 0. So that simply means that y is equal to 0, or y is equal to plus or minus square root of 2 if you go the same way like we did before. So you can see we can collect so many things here. So we can say that the critical points are, so we can collect all these values in different ways. So you can take 0, you can take 0 here and 0 here and just keep going like that. So the critical points so we have the possibility of 0, 0. Okay, we can have root 2 plus root 2 comma 0. We can have minus root 2 comma 0. What we are simply saying is that x can be 0, so we can have 0 and the 0 here. We can also have we can have this root 2 plus root 2 and minus root 2 here with the 0 down here. That's what we have so far. And then we can also go on and have so you can also go ahead and have, so we have 0, 0, root 2, 0, minus root 2, 0. We can also have 0, root 2. Okay. Again, we have 0, root 2. We can have 0 minus root 2, because here we have plus or minus root 2 again on the y side. Then we can have root 2, because we can have root 2. We can have root 2. We can also have root 2, root 2. We can have root 2 minus root 2 for x and y like that. We can have we can even have minus root 2, and we can have minus root 2 minus root 2. So we have this possible, so because it's a convex function, these are the possible critical points. As you can see from the function, it's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If you look at the graph again, the way we visualized it before, you can see this possibility. Like we have 9 possibilities. This is like 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Like you have that serious possibility going on there. So it's just a lot. Okay. So these are the possible critical points we can have in that place. So that takes us to step 2. So we have step 2 now, where we classify critical points. And the way to classify that is to do the second derivative test. Second derivative test. Okay. So we do the second derivative test. So what we simply do here is to compute the second order partial derivatives. Partial derivatives. So you remember that fx is what is that now? 4x cubed minus 8x. Fx is 4x cubed minus 8x. So that means that you have fx. When you differentiate again with respect to x, you get 12x squared minus 8. Then when you differentiate that fx with respect to y, so you get 0, because there's no y in that place. So this gives you the second order derivatives. On the other hand, you have fy to be 8 to be 4y cubed, 4y cubed minus 8y, like that. So that means that 4y with respect to x, there's no x, so we have 0. And you have 4y fyy, that is 12y squared minus 8. And then we have this, right? So we can form a Hessian matrix from this. So we have that the Hessian matrix is H which is equal to, of course, as usual, that's like fxx, fxy, fyx, fyy. That's how it is. And that is, so fxx in this case is 12x squared minus 8. So this is 12x squared minus 8. This is 0. And this is 0 again. And this is 12y squared minus 8. So usually you know that fxx and fyx, they are usually the same. So that's why we always have that issue. Interestingly, if you look, so this is the diagonal matrix, meaning that you only have elements along the principal diagonal, this place. So as a result of that, the determinants are just the values along the diagonal like that. So here we go ahead and say that, I mean the eigenvalues, not determinant. So here we now say the determinant of H of the Hessian matrix is that H, which is equal to, and you need to find the determinant. That's you multiply the diagonal elements. So the determinants will be equal to 12x squared minus 8 into 12y squared minus 8, like this. So we can now begin to evaluate one after the other. So we know that at 0, 0, right? When x is 0 and y is 0, so we see that the Hessian is basically equal to, so the Hessian, because x and y is 0, so we just have minus 8, 0, 0, minus 8, okay? So minus 8, 0, 0, minus 8. That's what we have there. So which is negative definite, because this is an eigenvalue, this is an eigenvalue, meaning they are negative, right? Which is negative definite. And when it is negative definite like that, so you're going to get a saddle point, basically. You're going to get a saddle point. Then on the other hand, if you now take all the other ones if you take plus or minus square root of 2, 0, and 0, plus or minus root 2, So if you use any of this there, you're going to get H to be something like 16, 0, 0, minus 8. Of course, because of the squares, right? So if you take, let's say if you take plus 2 and 0, okay? So plus 2, square root of plus, whether it is plus or minus even. So if you take plus or minus root 2, once you square it, it becomes 2. So 12 times 2 is 24. 24 minus 8 is 16, okay? And then you're also going to have 16 here. Or, I mean, there you have, so you have that the same thing there, and at the end of the day you have something like this, okay? So for this particular grouping, so in this case now, because it's not negative, it's not positive, you definitely have this is, so which is indefinite, because you have a mixture of positive and negative, so it is indefinite. So you also have saddle points, okay? You have saddle points. So the third grouping you can have is where you have both together being plus or minus 2. So at plus or minus root 2, plus or minus root 2. So you see that the Hessian matrix would simply be 16, 0, 0, 16, like this, okay? Which is positive definite because the eigenvalues are both positive. So, and that's the condition for convexity. So, which is positive definite. And because they are positive, right, we have local minima. Because they are greater than 0, we have local minima, okay? So, and this local minima now will now, I even think that this one should be local maxima, the first set, because they are both negative, you know. So I think they should be local maxima, but I mean, I have questions on this. You may want to check that out, but I think it should be local maxima. I want to believe so. Okay, so that takes us to step three. Step three now. So, but of course, we need minima for whatever. So we need minima, and we got that with this case where you have plus or minus root 2, plus or minus 2. So we can conclude, that's the conclusion as far as the iteration is concerned. So we say the function has local minima. The function has local minima at plus or minus root 2, comma, plus or minus root 2. Okay. Uh, and non-convex functions, since non-convex functions may have multiple minima. Okay. So global optimization techniques, okay, like simulated simulated annealing, or genetic algorithms, genetic algorithms can help verify if this the absolute lowest points, the absolute lowest points. Okay. As usual, we want to see the Python side of things. Let's see what Python has to say about this. Okay. Okay. So we have the code right here. So again, the function is defined in line 5 and 6, so to speak, and the derivatives are in lines 8, 9, and 10. Then we have the gradient descent parameters, the learning rate, that's like the step size, like we like to say. The momentum is 0.9, number of iterations is 50. And the number of iterations will determine a lot, and then the tolerance limit also. So with by changing the number of iterations, we can get better and better results, right? Then you also initialize the randomly. So you're going to have a random seed that ensures that with the same parameters, you always get the right answer. So you can study this code. You can copy it from Facebook on my timeline and then run it and see what happens. So I'm running this now. So you see in 50 iterations, we are expected to get like plus or minus square root of 2. Square root of 2 is 1.41414141414141. So after 50 iterations, x is minus 1.42, blah, 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 and y is 1.37. So you can see x is close to it. Y is also close, but not as close as it should really be. So what I'm going to do is I'm going to come here and increase the number of iterations to say 100. And you see that the results will be closer to what we have. So now we have x is minus 1.41, and this is also now y.41. That's minus like square root of root 2 and plus square root of root 2 for the y side. And then the function itself, the value is getting close to 4 as much as possible. So I can go ahead again and maybe even make it like 1,000 iterations for even better results, right? And as that is happening, the contour line is also adjusting accordingly. So imagine this is a lot of iterations. So you can see it's now like minus 1.41421, minus 1.41421. And then the optimal solution is something, the minimum of that function is now like minus 4 point something zero. So it's the convergence is this is what it converges to, like in about 301 iterations. And look at the contour line representing all of that. So the start point is the green line, while the red line, which you can't see because the blue lines have covered it. So it's like it's searching within that region, because the results can be all over the place. So it just keeps, so you can see a lot of, so this is more like 301 iterations, like 301 searches. And the more it goes, the better the result gets, basically. And that's what we are. So basically we see that the optimal solution is that x is minus and y is plus, and f of xy is minus 4 if you evaluate at those points. So we can go back and make that report. Okay. Okay. Um, so what have we said? So we have said all this, right? Look, I could just do it again. Results from the Python code. Result from the Python code. Okay. So it is that x is equal to, x is negative, I think. X is minus square root of 2, and y, or maybe I should put it in a more compact way. So optimal solution is, or let me say the optimal solution. Okay, allow my perfectionistic tendencies. Okay, so the optimal solution, the optimal solution is the optimal solution is x comma y equals minus square root of 2, and then square root of 2 with the objective value function, the objective value function being f of minus root 2, f of minus root 2 comma root 2 equals minus 4. Okay, that's what we have there. All right, so before we go again, I mean, I'm just going to do the practice question I gave the other time, which was meant for 2 dimensions that I gave on the other in the other video. So I guess I want to just repeat some of that here as much as possible. So obtain and classify, that's one. Obtain and classify the critical points of the function f of xy equals x cubed minus 3x y squared. Okay, that's one. Two, what else can I do here? Okay, let me repeat some of those questions. Solve the minimization problem numerically for f of x comma y equals sine xy plus x squared minus y squared. That goes. And then let me say number 3 now. Okay, number 3, find all local minima of f of x comma y equals cos x plus cos y plus xy. That's number 3. Number 4, let me do the machine learning question I did the other time. Question 4, in training a neural network, the loss function is given by L of W1, W2 equals e raised to minus W1 squared minus W2 squared plus W1 minus 1 squared plus W2 plus 2 squared. Okay, so the question is to explain why simple gradient descent may struggle with convergence. Okay, so that's how that has been. Please let me see your question in the comments, your answers to these problems in the comment section. Then feel free to get the Python code on my timeline on Facebook and try it out. try out all of these questions using the Python code. Let me also know how helpful these videos are for you. And if you have a question or topic you'd like me to teach, also let me know in the comment section, whether on YouTube or on Facebook. Then don't forget to subscribe if you have not done that already. If you have done that, thank you. If you have not, please go ahead. And if you have subscribed or you have not subscribed, and after subscribing, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And also like and share so that more people can have access to this content. And there's still more to come. I think I have about 4 topics for non-linear programming, problems under numerical optimization problems. Till I come your way again, keep doing maths right. Bye.